Good morning, Honors Math 2. Today is Tuesday, March 31st, and we're moving on to our third conic section. So far we've seen the circle and a parabola, and today we start our third conic section. So you should have the 8-7 task handy, but we have a couple visuals first. So this is where we're at so far. All of our conic sections come from when a plane, a flat surface, intersects a double cone. We saw this one first. If I could slice my cone with my plane, my flat surface, parallel to one of the faces of the cone, and if I could chop off the top of that cone and look at the cross section that's left, I formed that circle. If I could take my flat surface, my plane, and slice my cone parallel to one of these slant heights over here, parallel to the slant height, and if I could take off this side of the cone and look at that cross section, I would see a parabola sitting there on that cross section. Our third conic section is formed when I cut my cone so it's not parallel to one of the faces. So it's slanted like this. If I could slice that bottom cone and then take that part of the cone off and look up at that cross section, try to imagine for a second what shape I would form if this plane was not parallel to one of those faces. What would that cross section look like? Some of us start to say it would look like an oval. And that is our third conic section. An oval. Fancy name for an oval is an ellipse. And in this time that we have at home, I actually took a few moments and made an ellipse maker. So this is the definition of an ellipse. Let me jot it down for a second so you can think about this as we create an ellipse. We define all conic sections in terms of distances. If you remember, a circle is the set of all points whose distance from the center is always the same. A parabola is the set of all points whose distance from a focus and a directrix is always the same. An ellipse is the set of all points. An ellipse is the set of all points, the sum of whose distances from two set points. These are my two set points, these two little tacks. Those are my two set points. This is the sum of the distances, which is always the same. If you add this distance plus this distance, that's the same as adding this distance plus this distance, which is the same as adding this distance plus that distance. These two nails we call the foci. We call this F1 and F2. One focus for two foci, we call them. So rather than a center of a circle for an ellipse, we have two of those focus points. We call the length of this string the sum of those two distances, D, and we call it 2A. Okay, let's see if I can do this and form my ellipse with my ellipse maker. So notice that if I pull this tight, these are the two distances we're talking about, and the length of that string is 2A, if you add those two distances. And if I could keep the sum of those distances the same, and cruise around, I have to pick up my marker for just a second. Notice the sum of this plus this is remaining the same for all of these points. If I can keep that sum of those two distances the same all the way around, and there we go. And that's the shape that we form, and that's a nice little ellipse. The sum of the distances is always the same. We call this length of the string, the sum of those distances, 2A. This plus this is 2A. Please notice that if I could pull it this way, and then all the way to this way, this is my horizontal axes and vertical axes. In a circle, those axes are the same length. In an ellipse, they are not. Vertical axes, horizontal axes. I don't know if you can see, but the length of this horizontal axis containing those foci, if I could chop that little piece of string off and bring it over here, the length of that axis actually is 2A. This is that distance. So we say from the center of the ellipse to the edge is A. Sometimes we call the endpoints of that ellipse the vertices, so that's a vertex of the ellipse, and that is a focus of the ellipse. So that half the length of this horizontal axis I call A, and then we're going to label this vertical axis as B. Okay, you can always go back and look at some of these labels, and we're going to see them again in this task. All right, but an ellipse is the set of all points, the sum of whose distances from those two set points is always the same. The sum of those distances. I'm going to come back to this picture now and then. Okay, can you take a moment and turn, after our ellipse maker, we got all the way to number 13 of our task. So please find number 13 in task 8-7, and we have a nice little visual of that ellipse maker. I'll take my time as you find number 13. Notice these were those little tacks on my drawing, those foci. Sometimes we call these endpoints over here the vertices of my ellipse. And all of those distances are then labeled. There's that string. The sum of those two distances, in this case D1 plus D2, is always a constant distance. And we call that distance 2A. Alrighty, so there's our visual. So let's define a couple of things. A is always defined as the horizontal distance from the center to the vertex. B is defined as the vertical distance from the center, I can call that the center of my ellipse, to the ellipse. And C we define as the distance from the center to the focus. Center to focus is always C. I should label that on my ellipse maker. The distance from the center to the focus is always C. And we'll come back to that. Alrighty, can you pause for a second and make a couple observations? What do you notice about 2A, 2B, and 2C? Let me pause and you can write something down. Okay, I would jot down something like this. 2A is always the length of the entire horizontal axis. This is A. 2A is the entire horizontal axis. 2B, if I double it, is always the length of the total vertical axis. And that's C, and this is C. So 2C is the distance between the two foci, those two focus points we started with to create our ellipse. What is the mathematical relationship between A, B, and C? This is important to notice. Please notice that if I could pull that string straight up from those foci, straight up to the end of that vertical axis, I form this right triangle in here. I'm going to go back to my ellipse maker so you can see that right triangle. So if I could pull that constant sum straight up, I get this right triangle right in here. And it's important to notice what was the length of that string. Remember the length of my string, that constant distance was 2A. We defined it to be 2A. So this length of that half a string is A. So then this vertical distance is B. Half of that string, if I could pull it tight, is A. And I get that little right triangle right in the middle of my ellipse. And I can use the Pythagorean theorem. It's an odd version of the Pythagorean theorem. It's actually b squared plus c squared is always equal to a squared. Let me jot that down. In that ellipse, we notice, defining those lengths as we did, that b squared plus c squared is always equal to a squared, if you want to label that as a. Okay, so this is a good reference. Keep that in mind. I'm going to turn the page. The standard equation of an ellipse is not super easy to derive. This is the standard equation of an ellipse. We will write as x squared over a squared plus y squared over b squared is always equal to 1 when the center of our ellipse is at 0, 0. I'm going to define what a, b, and c are so you have it right next to that standard equation. Okay, so that for an ellipse centered at 0, 0, here's the standard equation where A is the horizontal distance from the center to the ellipse, B is the vertical distance from the center to the ellipse, and C is the distance from the center to the focus. So really, if I want to write the equation of this ellipse, standard equation, center at the origin, x squared over a squared plus y squared over b squared, and ellipse is always equal to 1. Can you take a moment and find A and B in this first ellipse? Okay, in this first ellipse, my horizontal distance was 6 from the center. My vertical distance was 5 from the center. So A squared is 36, B squared is 25, and that's the equation of that first ellipse. Notice the difference between an ellipse and a circle. In an ellipse, those are different, but in a circle, of course, you'd have a constant distance from that center. This is how we get an oval shape. Find A and B in that second ellipse, and please jot down the equation. Okay, in the second ellipse, horizontal distance A is 5, vertical distance B is 3, giving us a standard equation of x squared over 25 plus y squared over 9 is equal to 1. Over tomorrow, we'll see how we use that C value also for our focus. Let's see, can you look at that last ellipse on this page and think about what A is, think about what B is, and what that equation might be. Okay, please notice in this case that A is 4, that horizontal distance, so A squared is 16. B is 6, that vertical distance, squared is 36, and there's that standard equation. We call the longer axes typically the major axis. Please notice here that the major axis is vertical, which we certainly could have done that if I had turned my nails right at the beginning vertically instead of horizontally, and the vertical axis would be the major axis. Alrighty, let's look at that last case, please. And this is what we shift to tomorrow. What if we move that ellipse away from the center? If we move the center of that ellipse away from the origin. Could you guess what the equation of this ellipse might look like based on what we've done with circles and parabolas? Let me pause for a second. Now my center is at 7, -2. Think about what the equation of that ellipse might look like. Notice A, the horizontal distance from center to the ellipse is 4, so that denominator under the x is going to be 16. Denominator under the y corresponds to the vertical distance, that y movement. B is 3, b squared is 9. But since I'm not at the origin, I'm not just going to have an x squared and a y squared. Similar to a circle, I'm going to have an x minus 7 squared, y plus 2 squared. When I plug in that center, which we're again going to call HK. And that becomes a standard equation of an ellipse looking like x minus h squared over a squared plus y minus k squared over b squared equal to 1. Can you find one point actually on the ellipse and plug it into that equation and see what happens? Plug in an actual point on that ellipse. I will pause. I found this point, 7, -5, is actually on my ellipse. Notice what happens when I plug in 7, -5 into that equation that we just found. -5 plus 2 squared over 9 equal to 1. That's 0 over 16 plus -3 squared over 9 equal to 1. That's 0. That's 9 over 9, which is equal to 1. And it works when we plug into our equation. Alrighty, this is just a taste of some ellipses. We are going to move on tomorrow to do some more manipulating with that standard equation of an ellipse. Let's see, assignment tonight is the 8-7 RSG odds. You might have a couple questions that we will answer tomorrow. I will assign the evens tomorrow. I just don't know if we're quite ready to do all of it tonight. Alrighty, so 8-7 RSG odds tonight. Have a good day, and thanks for watching with us. And I will ask you to take a few pictures by the end of the week and submit them for some homework points. As long as I have 1 minute, please remember in this time, so far grades are not, are all in the grade book as no count. If something goes in the grade book and you want it to be counted in your grade, just shoot me an email and I will change it from no count to count in your grade. Have a good afternoon and thanks for watching. Bye-bye.